So here we have three sums, Sn, S2n and S3n. These sums are the sum to the nth term, 2nth term and 3nth terms of a given geometric progression. We need to show that the following expression is true. So let's begin. First we will specify the first term and the common ratio. So let the first term be represented by the letter A in lowercase and the common ratio that will be represented by the letter R in lowercase as well. Now we know that the sum up to the n terms of a given geometric progression Sn, so that's given by the first term A multiplied to R raised to the power of n minus 1 whole divided by R minus 1. Then we can also define the sum to the 2n term, which will be equals to A, the first term, multiplied to R raised to the power of 2n minus 1 whole divided by R minus 1. And then we have S3n, which will be the sum to the 3n terms, that will be A multiplied to R raised to the power of 3n minus 1 whole divided by R minus 1. So now that I have the three sums, so let's start from the left hand side. On the left hand side we have Sn, so this is multiplied to S3n minus S2n, which will be equals to, so we'll substitute the value here. So we have A multiplied to R raised to the power of n minus 1 divided by R minus 1, which will be multiplied to S3n, so that's A times R raised to the power of 3n minus 1 divided by R minus 1 minus A times R raised to the power of 2n minus 1 divided by R minus 1, which will be equals to, so we can take A over R minus 1 as the common factor from within the parentheses, so we will get A squared multiplied to R raised to the power of n minus 1 E divided by R minus 1 whole squared, and within the parentheses we are left with R raised to the power of 3n minus 1 minus R raised to the power of 2n plus 1. So here negative 1 and positive 1 gets cancelled, and we are left with R raised to the power of 3n minus R raised to the power of 2n within the parentheses. So that means we will now have, now we're going to take R raised to the power of 2n as the common factor from the two terms within the parentheses. So this is going to leave us with R raised to the power of n minus 1, which will be equals to, so now we will have A squared multiplied to R raised to the power of 2n times, so R raised to the power of n minus 1 whole squared divided by R minus 1 whole squared. So this can be also represented as A multiplied to R raised to the power of n multiplied to R raised to the power of n minus 1 whole divided by R minus 1 whole squared. In the next step, what we'll do, we'll keep A over R minus 1 common. Now we will multiply R raised to the power of n to each terms within the parentheses, so we're going to get R raised to the power of 2n minus R raised to the power of n whole squared, which will be A divided by R minus 1 multiplied to, so we can rewrite the expression within the parentheses as R raised to the power of 2n minus 1 minus R raised to the power of n minus 1. So this can be split into two parts, so there is a whole square as well. So this can be split into two parts as A times R raised to the power of 2n minus 1 divided by R minus 1 minus A times R raised to the power of n minus 1 divided by R minus 1 whole squared. And we've already defined this as the sum to the 2n terms minus, and this will be the sum to n terms whole squared, which is the expression on the right hand side. So hence we have successfully showed that Sn multiplied to S3n minus Sn, that this is equals to S2n minus Sn whole squared.